Welcome back. Please share, subscribe, and comment. In mathematical physics, the Berezin integral, named after Felix Berezin, also known as Grassmann integral after Hermann Grassmann, is a way to define integration for functions of Grassmann variables, elements of the exterior algebra. It is not an integral in the Lebesgue sense. The word integral is used because the Berezin integral has properties analogous to the Lebesgue integral and because it extends the path integral in physics, where it is used as a sum over histories for fermions. Definition: let lambda n be the exterior algebra of polynomials in anti-commuting elements theta 1, theta n over the field of complex numbers. The ordering of the generators theta 1, theta n is fixed and defines the orientation of the exterior algebra. One variable, the Berezin integral over the sole Grassmann variable theta equals theta 1, is defined to be a linear functional integral. AF theta plus BG theta d theta equals a integral f theta d theta plus b integral g theta d theta. B is an element of C where we define integral theta d theta equals 1, integral d theta equals 0, so that integral del theta f theta d theta equals 0. These properties define the integral uniquely and imply integral a theta plus b d theta equals a. B is an element of C. Take note that f theta equals a theta plus b is the most general function of theta because Grassmann variables square to 0, so f theta cannot have non-zero terms beyond linear order. Multiple variables, the Berezin integral on lambda n is defined to be the unique linear functional integral lambda n d theta with the following properties. Integral lambda n theta n midline horizontal ellipsis theta 1 d theta equals 1. Integral lambda n del f del theta I d theta equals 0, I equals 1. N for any f is an element of lambda n, where del theta I means the left or the right partial derivative. These properties define the integral uniquely. Notice that different conventions exist in the literature. Some authors define instead integral lambda n. Theta 1 midline horizontal ellipsis theta n d theta equals 1. The formula integral lambda n f theta d theta equals integral lambda 1. Midline horizontal ellipsis integral lambda 1. Integral lambda 1 f theta d theta 1 d theta 2 midline horizontal ellipsis d theta n expresses the Fubini law. On the right-hand side, the interior integral of a monomial f equals g theta. Theta 1 is set to be g theta, where theta equals theta 2, theta n. The integral of f equals g theta vanishes. The integral with respect to theta 2 is calculated in a similar way, and so on. Change of Grassmann variables: let theta I equals theta I, psi 1, psi n, I equals 1. N be odd polynomials and some antisymmetric variables psi 1, psi n. The Jacobian is the matrix D equals del theta I del psi j. I, j equals 1, and where del psi j refers to the right derivative del theta 1 theta 2 del theta 2 equals theta 1 del theta 1 theta 2 del theta 1 equals minus theta 2. The formula for the coordinate change reads integral f theta d theta equals integral f theta psi det d minus 1 d psi. Integrating even and odd variables definition: consider now the algebra lambda m divides n of functions of real commuting variables x equals x1, xm, and of anti-commuting variables theta 1, theta n, which is called the free superalgebra of dimension mn. Intuitively, a function f equals fx theta is an element of lambda m divides n is a function of m even, bosonic, commuting variables and of n odd, fermionic, anti-commuting variables. More formally, an element f equals fx theta is an element of lambda m divides n is a function of the argument x that varies in an open set x subset of Rm with values in the algebra lambda n. Suppose that this function is continuous and vanishes in the complement of a compact set K subset of Rm. The Berezin integral is the number integral lambda m divides n f x theta d theta dx equals integral Rm dx integral lambda n f x theta d theta. Change of even and odd variables: let a coordinate transformation be given by xi equals xi y psi I equals 1 m theta j equals theta j y psi, j equals 1, n, where xi are even and theta j are odd polynomials of psi, depending on even variables y. The Jacobian matrix of this transformation has the block form j equals del x theta del y psi equals abcd, where each even derivative del yj commutes with all elements of the algebra lambda m divides n. The odd derivatives commute with even elements and anti-commute with odd elements. The entries of the diagonal blocks a equals del x del y and d equals del theta del psi are even, and the entries of the off-diagonal blocks b equals del x del psi, c equals del theta del y are odd functions, where del psi j again mean right derivatives. When the function d is invertible in lambda m divides n, j equals del x theta del y psi equals abcd equals ib0d, a minus bd minus 1c0d minus 1ci. So we have the Berezinian or superdeterminant of the matrix J, which is the even function brj equals det a minus bd minus 1c. Det d minus 1 suppose that the real functions xi equals xi, y, 0. Define a smooth invertible map F. Yx of open sets x, yn are M, and the linear part of the map psi, theta equals theta, y psi, is invertible for each y is an element of y. The general transformation law for the Berezin integral reads integral lambda m divides nfx theta d theta dx equals integral lambda m divides nfx y psi theta y psi epsilon brj d psi dy equals integral lambda m divides nfx y psi theta y psi epsilon det a minus bd minus 1c det d psi dy, where epsilon equals sgn det del x y 0 del y is the sign of the orientation of the map F. The superposition fx y psi theta y psi is defined in the obvious way if the functions xi, y psi do not depend on psi. In the general case, we write xi y psi equals xi y 0 plus delta I, where delta I equals 1. M are even nilpotent elements of lambda m divides n and set fx y psi theta equals fx y 0 theta plus sigma I del f del xix y 0 theta delta I plus 1 2 sigma I j del 2 f del xi del xj x y 0 theta delta I delta j plus midline horizontal ellipsis, where the Taylor series is finite. Useful formulas. The following formulas for Gaussian integrals are used often in the path integral formulation of quantum field theory. Integral exp minus theta ta eta d theta d eta equals det a, with a being a complex n times n matrix. Integral exp minus 1 2 theta tm theta d theta equals pfm in even 0 n odd with m being a complex skew-symmetric n times n matrix, and pfm being the Pfaffian of m, which fulfills pfm 2 equals det m. In the above formulas, the notation d theta equals d theta 1 midline horizontal ellipsis d theta n is used. From these formulas, other useful formulas follow. See Appendix AN. Integral exp theta t a eta plus theta tj plus k t eta d eta 1 d theta 1 d eta and d theta n equals det a exp minus k t a minus 1j, with it being an invertible n times n matrix. Note that these integrals are all in the form of a partition function. History. Berezin integral was probably first presented by David John Canlin in 1956. Later, it was independently discovered by Felix Berezin in 1966. Unfortunately, Canlin's article failed to attract notice and has been buried in oblivion. Berezin's work came to be widely known and has almost been cited universally, becoming an indispensable tool to treat quantum field theory of fermions by functional integral. Other authors contributed to these developments, including the physicist Kalatnikov, although his paper contains mistakes, Matthews and Salam, and Martin.